All right, so yeah, so like I said, tokenization, it takes an input and it converts it to a flat stream of tokens. So that makes it a lot easier to work with because, like I said, it like condenses multiple characters into just one token. It also removes spaces, tabs, and new lines. Also comments generally, um, and then it like pre-processes things like numbers, float strings, and then also things like identifiers, like variable names and keywords like if, then, or else. So when we interpret our program, we don't want to treat if, then, and else as separate characters. It's easier to think about them as one word. Um, yeah, so this basic Rust script program is kind of like a ternary expression, but um, it runs if 5 is less than 10, then it returns yes, otherwise it returns no. Um, One thing that I didn't mention about Rust script earlier is that it's completely expression based. There's no concept of like something that does another thing and doesn't return anything. Like everything returns something. So even an if expression is going to return something, which is why this whole expression here, it will evaluate to yes. It's not just like throwing away the result. Um, yeah, and so we can see how this is tokenized. It's like pretty straightforward. We take the if, number 5 less than else. I forgot a few commas, but that's okay. Um, yeah, so then parsing is the more interesting step. Um, and so it brings up this really important concept of the abstract syntax tree that I talked about earlier, where your whole program is represented as a tree, um, and it's like very recursive. So here we can see a little bit more clearly. This if expression, it contains other expressions inside of it. So the condition is a binary expression, um, and then these are like simpler expressions, but they're still expressions. And again, we can pretty clearly see how we would go about evaluating this, like recursively. Um, yeah, so we'll get to that in a second. And by the way, I wanted to just point out the code for this is like pretty simple. Um, like when you hear about writing parsers, you might hear that like a parser is like very scary, confusing. It's not that bad. It's just like very annoying. So here, this is parsing an expression that's of the form like let x equals 5. So this eats the identifier. Um, it checks if it's actually an identifier. Otherwise, it throws an exception. Then it makes sure that the next token is an equal sign. And then finally, it parses the expression on the right hand side. And again, this is like an overview. You're not meant to like fully understand it. Uh, but you can see how the thing that you want to parse like pretty directly maps into how you actually write the code. All right, so next is the interpreter, which is like the most complicated step, and it's kind of the part that will like glaze over the most in the workshop. But basically, we're just taking our tree and we're stepping over it. And I think, yeah, I have a more detailed example here. Here. All right, so we have this like basic if expression again. If x is less than 10, then it returns x plus 15. Otherwise, it returns invalid input. So that's gonna get parsed to this tree, and this is written as if it's like a Java class because that's what we'll be working with. But really, this is how we would want to draw the tree out. So it's a single if node which has 3 children. One of them is a condition, one of them is then, and one of them is else. And again, each of these can be another expression. Like you can have if expressions inside of if expressions, etc. Yeah, so how we would evaluate this is first look at the condition, is x less than 15? We would have like a dictionary that like tells you what each variable is. So let's say x is 5, then this would evaluate to 5. This is already 15, so this would be true. Okay, you get the idea. It's hard to write on this. Yeah, and then because it's true, then we know that we would evaluate the then expression instead of the else expression. So we recurse onto the then, and we see it's a plus node, and it has the variable x, which is again 5, and the constant, okay, I typed something wrong, but 15, so it should be 20. And then this would like, okay, so you can't run the REPL until we finish it. That makes sense. All right, so to start out with, adding a feature to the language, like any feature, we kind of work like tokenizer to evaluator, like we talked about before. So first we have to scan it, then we have to parse it, then we have to evaluate it. So first, scanning it is pretty simple. We just have to convert our keywords into tokens. And so we're going to look at tokenizer.java and also maybe token.java. So tokenizer is like pretty long. Again, you don't have to understand all of it right now, but it's not too complicated that you wouldn't be able to understand it if you spent like a few minutes on it, just time that we don't have right now. But basically, it's just got some like big switch statements. There's one here, and then there's one like below, or yeah, this one. So here we just have this thing that says, if it finds an if string, then throw an exception. Instead, we're going to want to make that actually return a token. So the token is called if, and we just pass in lexeme for unimportant reasons. So once we have this implemented, when we run it, it's not going to say unimplemented tokenizer, it's going to say unimplemented parser, probably. Yeah, so now it says that the parser is unimplemented. So I'll wait a little bit for you all to type this. All right, anyone still working on that? Okay, and also I just wanted to point out the way the token types are like described or whatever is here. There's just like a big list of them in an enum. So yeah, it's pretty straightforward. All right, so now that we've scanned the if expressions, we need to parse them. Oh yeah, and I forgot to mention, we also needed the then and else here, but I just did them because it's not too complicated. Yeah, so now that we've scanned it, we can parse it. The parser is gonna do like the same process we talked about earlier, where it's just gonna recursively call itself. And there's a bunch of helper functions if you go to parser.java. There's like all of this, but then there's like this parse import expression, there's parse match expression, parse list, parse block, and then there's parse if expression somewhere. I said that's on line 110. Yeah, so parse if expression right now is just throwing an exception. And I wanted to show that where we get the parse, like where we actually call parse if expression, is that there's this big switch statement again, and whenever we see a token that says if, we know that the only valid like result that starts with if is an if expression. So that's why we just call this. There's like nothing magic here at all. So back to here. Yeah, so when we look at what our like syntax for an if expression is, it's gonna be first there's an if token, then there's an expression, then there's a then token, another expression, then there's a else token, and another expression. So our code is gonna like pretty closely follow that. So actually what happens is that the if token is already taken up by that switch statement we saw earlier. We already know that it starts with an if token. A funny like thing that I don't know, the only term I know for like consuming the tokens is just eating them. So yeah, so the condition expression is next, and so all we do is we say expression condition equals x per bp 0. So this is like kind of confusing, but x per bp is like, it stands for expression binding power. It just parses any expression. It could just be called parse expression, but the argument it gets is to set like the precedence, and that matters when we have like operators, like addition and multiplication with different precedences. When we have the conditional of an if expression, we want that to have like infinite precedence, like anything inside, or not infinite, we want it to have 0 precedence, because anything inside is like its own expression. It doesn't care what operators came before it. So that's why we're giving it 0. Yeah, so then we have the then token, and so we're just gonna assert next that it's a then token, and the code for assert next is like very simple also. It's up here. We just eat the token and then throw an exception if it's not what we expected. So again, there's like no magic here at all. Again, we're gonna take the then expression, and then you can probably see the pattern. Oh. Yeah, so now we have all of our variables for the if, then, and else expressions. So we need to construct a node, which is just an if. This is a class, so we're calling the constructor, and it's gonna have the cond then, and we actually can't call this else. Because that's a keyword. Yeah, so this is all we have to do to parse it. So a lot of the time when people are talking about like a parser being like scary and confusing, it's just because it's like kind of brain dead. A lot of it is really tedious and it's just not fun. But luckily, the rest of writing interpreters is a lot more interesting. Yeah, so I'll wait a little bit for you all to get that. And by the way, if we run it, it will now say that the evaluator is unimplemented. Oh, I also did this wrong. This should not be if, this needs to be if expression. Oh, okay. This is kind of unsatisfying, but it also needs um, this these two variables, which are um, so these are like kind of optional. The last two parameters, um, they're basically used for um, like error handling. So when we parse an expression, it's best that we tell it like where it is in the code, because then we can, like, if the interpreter errors because your code is wrong, we can use that to tell the user where the error is. So nx.index is just like the start index of the first token, and then else expression.endIndex is the last index of the else expression, which is also the last index of the overall if expression. And yeah. Oh, I still did that wrong. This is oops. It should be end index. Is everyone else also getting this error, by the way? Okay, I typed something wrong. Oh, forgot to call new. Is that it? Okay. Yeah, it's a constructor, so we have to use new. That's an example actually of like the Java compiler not setting the index and end index well, because it should have given us like a different position for that error. It should have probably put it at the start of the expression instead of like inside of the arguments. Alright, so now it says unimplemented eval. And raise your hand if you're not here yet. Alright. Yeah, so now that we have implemented the parser, we can finally evaluate it. So one thing that I wanted to touch on is that every sort of like node in our graph here, with like the if, less, plus, else, whatever, they're all just classes that extend this abstract class. So it's just like a tree you would see in like CS 240 or anything. But each of the nodes can have like a different type, which is why we're just using inheritance to deal with that. So there's like atomic expression, which just has one value, which can be like an integer or a string or an array or something. There's a prefix expression that just handles like negation and like not. So basically any expression that has one prefix operator. There's binary expression, which is like plus, minus, any like comparisons. There's a bunch of them here. And this also makes it like pretty clear how interpretation works. We're just evaluating the left, evaluating the right, and then looking at the operator to see what to do with the result. Yeah, so there's block expression, which is just a list of expressions. And then there's if expression here. So this class, it has what we wanted, and we got this eval. So you guys can probably tell how this is gonna go, right? It's gonna go the same as what we did here. We're gonna first evaluate the condition, look at if it's true or not. And then we're gonna evaluate the then or the else depending on the value of the condition. So, let me actually pull up the code so I don't type anything wrong. Yeah, so first, eval returns an atom, right? Because we want everything to evaluate to a single value. So atom conditional result equals, actually I think, equals cons.eval scope. So scope is like a dictionary basically that has all the variables, and we need that to evaluate anything. Then we literally just use an if expression in Java. If conditional result that is truthy, which we'll look at in a second, then we're going to return, I called it left-hand side and right-hand side here. That should be straightforward, I guess. Yeah, so this is probably what you would expect. Is truthy is pretty simple. So, raise your hand if you're not done with this part. Alright, cool. This is not good. Is truthy is, this is the atom class, by the way, so this is kind of similar to expression. It's like a huge abstract class that has a bunch of instances, and yeah, so we check if it's a boolean, then return the boolean. If it's a list, then check if it's not empty, etc. Yeah, so now if we run this, it's gonna give us a smiley face. So now we have implemented if expressions. Yeah. So that's all it really takes to add a feature to a programming language. You can now probably like read all the code. It's a bit easier to read on GitHub than Replit, in my opinion. And you can probably like understand all of it. The most complicated parts of it are like calling functions is kind of painful because you have to deal with scoping issues. So yeah, so this like lambda call is a little bit complicated, or at least it's a little bit tricky, but you can probably figure it out. There's a lot of like edge cases with programming languages, and a lot of them are pretty difficult to catch because you just have to write like code in your language. But that's what like programming language research is really good for, because it gives us a bunch of tools to like verify that our language actually works. And yeah, so now that we've implemented like a full language feature, like front to back, we can look at some possible extensions. And by the this resource is Crafting Interpreters is like a really good book. It has you write an interpreter and a compiler. It would probably take like a summer to follow. It's pretty in depth. Um, but if you read like the first uh, like 11 or 10 chapters of it, that's like more than enough to understand anything you need. Um, I have a blog post. This is the code base. So this is the first version of the language, which is a lot simpler. It's like in a single file. I actually wrote it for CS180. But yeah, so it's like 1,000 lines or so. There's a lot of tests because of CS180 stuff. But then the code base that we actually worked on was this one, which is a more complicated fork. So if you just want to like understand the basics of the whole code base, you should read this one. But this one is like a lot more useful because it's a more complicated language. Yeah, and then these two links are by this guy called Linus Lee, who's actually from Lafayette, or, West Lafayette. He just has like really good blog posts on like programming languages. He wrote like 2 programming languages, and he writes his websites in his languages. Like he does a bunch of projects just using languages that he wrote, and that's really cool. And yeah, so for the rest of the workshop, you guys are gonna try to add more to this language. So in order of like difficulty, there's keyword swaps, which you can definitely do here. Essentially, we're gonna like switch keywords to something more interesting, like make it Purdue themed or something. And all you have to do there is look at tokenizer, and we have that big switch statement, and all you have to do is like switch these strings. And then there's also operators. So you can switch the operators around, or you can add an operator. If you add an operator, then you have to update the tokenizer, you have to add a token, you have to work with the parser to set its precedence. So like, does it get evaluated before multiplication or like after? And then you also have to evaluate it in expression.java, where you like tell it what it actually has to do. So one cool operator is like the pipe operator, which would take an expression like, instead of like f of x, you could write x is pipe to f. That's like a really cool operator to use, and it's pretty simple to implement because you just evaluate, or you use f's called method on x. And then there's like exponentiation is an operator. There's a few options. And then this is like the hardest one, but you could add a new primitive type. So right now RustScript doesn't have like dictionaries. You can add that first in atom.java. It will take like a bit of code. You have to write a whole class, and then you have to scan and parse it. Also vectors, which would be interesting because you wouldn't necessarily have to parse them any differently from lists. You would just have to change how like addition and subtraction are implemented. Yeah, and there's like a bunch of options. So if you need any help, just ask. And feel free to ask any questions now.